Welcome, ladies and gentlemen, to the Technical Forum of Hydrogen and Fuel Cells Europe at the Hannover Fair 2021. My name is Bernhard Jäckel. I'm the moderator on this stage, and we present you a lot of high-class presentations of the newest technology. The next technology presentation will be held of somebody from the Fraunhofer Institute of the ISE, the Institute for Solar Energy Systems. And I would like to invite you to pronounce the title with me. The speech is about methanol synthesis from steel mill gases. And the speaker, head of group powers to limit, is Max Hadrich. Hadrich.
Hi everybody, thank you for attending my talk on methanol synthesis from steel mill gases. My name is Max, I'm head of group Power to Liquids at the Fraunhofer Institute for Solar Energy Systems in Freiburg in the Black Forest in the southwest of Germany. Let me introduce to you methanol as a key PTX molecule used as carbon capture and utilization molecule. So the methanol synthesis is here right in the middle between the sustainable feedstocks and the advanced products. Methanol has a lot of downstream sectors where it can be used. On this chart by MMSA, we see just how diverse the methanol demand is. We have around 100 million tons per year of production, and it's continuously increasing. Methanol being a very good liquid energy storage, we expect this number to rise and the importance of methanol to become ever greater. It has great combustion properties. It can be produced directly from CO2 and hydrogen, so there's no issue of reverse water gas shift or so. So there's good reasons why there's a lot of projects going on worldwide and why we as Fraunhofer ISE want to learn more about this synthesis in detail. We're doing the approach in several levels. We're looking at the reactor side, we're looking at the process side where the reactor is integrated, and then of course the system where we have the largest perspective on everything. We have appropriate tools corresponding to the specific objectives in the different areas of work. And the way these tools interact can be seen on the next slide. We take great pride in our technical process models that we validate with real data from real plants, and that helps us to then use the models for our economic considerations, the input being what the customer asks from us or what the plant should do, and the result being a total product cost for the methanol. And today I will be giving you more information about the data that underlies this validated technical model. The two plants we used to create the data and to validate it are the Power to Methanol mini plant on the left side and the Carbon to Chem mini plant on the right side. The scale down mini plant is really unique as we can observe exactly what happens on the reaction level. Methanol synthesis is a reaction that happens in a large reactor with 5,000 tubes. Impossible to do in a research institute, of course. So first thing, we do a numbering down. We choose one of these tubes, but it's still too large for us, so we scale it down to have something that works well in our labs. Conserving some very specific particularities, some adimensional numbers, we can still use the results from this reactor in the scale-up and deduct properties of the industrial process. Here are some facts about the plant. It has a very broad range of operation, and we could study the dynamic operation in great detail. We were able to measure temperature profile with a fiber optic measurement every 2 or 3 millimeters, and the composition was measured by FTIR, so highly dynamic measurements there as well, with the objective being describing the kinetics very well and learning how a methanol synthesis can be operated dynamically. Having collected the data in the lab, we wanted to see if the model was transferable to a real-world application. And here, within the process, in the project Carbon to Chem, we ran an adiabatic mini plant with recycle at the ThyssenKrupp steel mill in Duisburg, one of the largest steel mills in the world, one of the largest CO2 point sources in the world. Steel mill gases are super interesting because they are an abundant source of carbon dioxide, of carbon monoxide, and hydrogen. And together with our partners, we ran this plant for several years. We designed and commissioned and operated it, but it was in Duisburg at the customer's location. The gas cleaning of these blast furnace gases was conducted by Linde and ThyssenKrupp Industrial Solutions. The catalyst was provided by Clariant. We could operate the plant for over 6,000 hours, producing several thousand liters of raw methanol, and with the objective being validating the process model we previously recorded and studying the long-term effects of such an operation. And the data I will be able to show you today is really first of their kind. To my knowledge, nobody has conducted methanol synthesis from blast furnace gas. Let me explain the chart because it's a little busy. So on the top graph in black, we have the wait time yield, so how much methanol is produced per unit of catalyst. Unfortunately, I can't show you the real numbers. It had to be normalized, but what you can see is that over these 3,000 hours, the catalyst performed in quite a stable way. There's no deactivation. That means that the gas cleaning is working well. There's no residual poisons. In green here, we have the methanol mass fraction. We're continuously monitoring the composition by measuring the refractive index. And you might ask, why is there still such a spread in the results? Why is it not a constant line? Well, that's because we're using blast furnace gas. And the blast furnace gas is a dynamic gas because the way the blast furnace is operated, the composition and the amount of gas that is available changes drastically. So in orange, for example, we have the carbon oxide ratio. That is the ratio between carbon monoxide and carbon dioxide. That changes over the time depending on what kind of iron ore or what kind of coal you have. And in blue, we have the inert composition, so how much nitrogen, how much methane is contained in this gas. This data is only a subset of what we've done. You see some blank spots. That's where we ran our campaigns. But this is the benchmark that we repeated again and again to see how well the reactor is performing over time. So I can proudly say that here our objectives were achieved. We compared the measured data, that's always on the x-axis, and the simulated data, that's on the y-axis, for several parameters: the wait time yield, the stoichiometric number in the loop, the inert content in the loop, and the carbon oxide ratio in the loop. The results have recently been published in Chemie Ingenieurtechnik, and there will be many more publications to come with the details. But what we can really say is, with our process model from an isothermal reactor, we were able to validate an adiabatic reactor, and that gives us very good hope that we can now, in the next stage, also describe large-scale reactors for industry. Let me come back again to this graph to give you an outlook. So really the next step is to design large-scale plants and provide accurate economic models for several locations around the world where we will be conducting methanol synthesis from renewable gases. Okay, next up for some conclusions, maybe for your report back home. Fraunhofer ISE offers validated models on different levels of detail. We can deal with process dynamics very well, as shown in the world's first demonstration of methanol synthesis from blast furnace gases. And if you'd like to discuss the results with me in more detail, you're very welcome in booth C39 for a cup of coffee and some discussions about the methanol synthesis. I'd like to thank our sponsors from the Federal Ministry of Education and Research who've been supporting this project Carbon to Chem. And of course, I'd like to thank all of you for your attention and the possibility to speak. I wish you a great Hannover Fair, and take care.
Thanks a lot for this good speak. Is there any question from the audience right now? There's time left. We have time for 1 or 2 questions. If not right now, you said it already, you're invited to come to C39, right?
Yes.
Thanks a lot, Max Hadrich.
Thank you very much.